Alright guys, piecewise defined functions here, and these are going to be basically just like they sound, functions that have different pieces to them. So you take a look, they have an example created for us already here, and they have the graph. Let's see if we can highlight a little bit here. Excuse me. So we have y equals x minus 2. That is the graph for x values that are less than 3. And then they have a different graph for the x values that are greater than or equal to 3. So the key feature here is to recognize that things change around x being 3. So here's x equals 3, right? So that x equals 3 is kind of like the borderline. That's where things change. Because again, notice there's one rule for x is less than 3, okay, which means on this side. And you can see the equation x minus 2, right? Here's the y-intercept of negative 2. The slope is 1. Okay, so this graph right here is y equals x minus 2. And that graph only applies when the x values are less than 3. Okay, this thing does not continue up here, right? That's not there. On the other side of 3, right, for x values bigger than or equal to 3, which is on this side, this is the equation of the graph. Okay, and as you can see, it would have a y-intercept up at 7, and its slope is negative 2. Down 2 over 1, down 2 over 1. Okay, so it doesn't start till there, though. We're not showing the part on the left, right? I'm not showing this part of it because this is like the restriction on x values. We're only showing the rest of the line right here. Okay, so it's two different lines being pieced together to form a single function. And if you remember, to be a function, it means that each x value, each input, has only one y value. Okay, and there's a way to test that you may have seen called the vertical line test. And basically what the vertical line test is going to say is that if a function, if you can draw vertical lines through the graph, it's only going to touch the graph once. So for example, okay, if you had a graph like, it's going to be easier to show you one that's not a function. If you had a graph like this, okay, notice a vertical line, like that for example, would touch the graph more than once. And what that's doing is showing that this definition, this property does not hold because whatever this x value is here, there are two y values with that x value. So you can use the vertical line test as a way to check if something is a function. Okay, but let's keep digging into these piecewise functions. Can we describe the graph that we just drew clearly as possible? So it looks like two different linear functions. Okay, we could say one of them had a positive slope, that green one, and this other one had a negative slope, that kind of thing. Okay, why is the graph a function? We just kind of talked about that. You could say it passes the vertical line test. That would be a good reason for that, as long as you know what the vertical line test is, and that's why we reviewed that. Oops, sorry guys, writing to get a little choppy here. We passed the vertical line test. All right, let's do another example. Okay, let's take a look. Can we graph our own? Y equals x squared minus 3 for x less than or equal to 0, and y equals 1/4 x plus 1 for x greater than 0. Okay, so let's first think about, this is kind of telling us where things are going to change. Okay, there's one rule when x is less than or equal to 0, and one rule for the x is greater than 0. So I'm just going to draw like a dotted line just because we're just starting out. Normally we wouldn't put that on the paper because it means something else if you have a dashed line like that later on. But for now, let's just do it as a reminder that we're going to have different graphs on each side. Okay, and one way to graph a function, if you don't know what it looks like, okay, like we might not be familiar at this point with y equals x squared minus 3. Okay, later on this year and beyond we will. But what you can always do is make a table of values and get some points to plot, right? So we know, we got to be smart though, the only x values I want to choose are ones that are less than or equal to 0. So why don't we do like -2, -1, and 0, and let's just see what the y's would be, and then we'll plot a few points. So if I plug those x's into the rule, it's x squared minus 3. So -2 squared is 4, minus 3 is 1. Okay, -1 squared is 1, minus 3 is -2. And then 0 squared is 0 minus 3 is -3. So let's plot those points. Now here's one other thing too. Notice when x actually equals 0, since we have that little equal sign right there, this is the rule we're going to use. We're not going to use the other rule. The other rule only applies when x is greater than 0. So that means at this point, when x is 0, y is -3, we're going to do a closed-in circle, not an open circle. Okay, and we'll see the difference in a second. But there's 0, -3. Okay, -1, -2 is here. -2, 1 is here. Okay, and this thing is actually going to continue. It's going to be like the left-hand side of what's called a parabola. Okay, the full graph would have looked like a U. Okay, and we'll get to know that stuff. This is a quadratic function because it had an x squared in it. But we're just showing basically just this left side of it because of the domain restriction. Okay, now the other side, the y equals 1/4 x plus 1, we should be able to graph that. We know about y-intercepts and slopes. Now this one, when x actually equals 0, this graph doesn't apply, right? When x equaled 0, we were using this point. Okay, ours here starts only when x is greater than 0. Now it doesn't mean you have to go all the way to the next whole number though. Okay, so what we do is we put an open circle. Here's the y-intercept. It would be at 1, but the circle's open, and then we apply our slope of up 1 over 4. And that linear piece ends up going like that. Okay, so that's our piecewise function. Again, we have the open circle here because this rule only applies when x is greater than 0, but you do not have to start at the next whole number. You don't have to go all the way to 1. Right, x could be 1/2, or x could be 0.1. Anything bigger than 0, that's why our graph actually starts here, but the circle is open. I don't know what just happened there. Let's try that again. It never gets below. It went back to the next page, and I was still thinking about the previous one. Hang on. Alright, so the way we write these things, let's go back to the top here, describe the graph. So it had a curved piece, the left side of a parabola, and then the right side was a linear function. And it was a function again, it did pass the vertical line test. Okay, so let's talk about these piecewise functions. This is going to be like the fancy way. This is how we would write. This is actually the one we just did. So we name the function f of x, and then you see they give it the fancy brace there. That lets you know that these two things kind of go together. This is one single function. And then you see the function rules, x squared minus 3 and 1/4 x plus 1. Okay, and then sometimes there's a comma there, or they just put the word if. And then it's called a domain restriction. So the domain of a function talks about which x values it applies to. Okay, so that's telling us where we use x squared minus 3, which is on the left side of our graph, okay, because that's where x is less than or equal to 0. And then when x was greater than 0, we used the 1/4 x plus 1. All right, why don't we graph another example here. Now this one is g of x equals -2x minus 2, and that applies when x is less than -1. And then the other rule is x plus 3 if x is greater than or equal to -1. So again, what you might want to do, just because we're just getting started, why don't we put the little borderline wall. There's x equals -1, right? I know there's going to be different graphs on each side. Okay, one thing we can do, again, we can make a table of values. Okay, and let's be careful though now. Think about if we use -4, -3, -2, and so on. The x values that are less than -1, which are these three, we need to use this first function rule, okay, because those x's are less than -1. So let's see what we get. So if I plug in -4, so -2 times -4 is 8, minus 2 is 6. If I plug in -3, -2 times -3 is 6, minus 2 is 4. If I plug in -2, -2 times -2 is 4, minus 2 gets me 2. Okay, now for the other points though, for these values, those x values are all greater than or equal to -1, so I need to be using the rule of x plus 3. Okay, so if I plug in the -1 plus 3, we get 2. If I plug in the 0 plus 3, we get 3. The 1 plus 3, and the 2 plus 3. Okay, now we have some points that we can plot, and I'm going to try and use the colors here. Let's see if we can zoom in and get a little bigger graph. Okay, so -4 is up at 6. -3 is at 4. -2 is at 2. Okay, then the other graph, -1 is at 2. 0 is at 3. 1 goes to 4, and 2 goes to 5. So this is a linear function with a slope of 1. Okay, the other side was also linear with a slope of -2. Okay, now here's the thing. I bet some people would stop right there, right? Or they would stop right at 1. But this red graph needs to apply for all x values less than -1. So it needs to go all the way, but have an open circle there. Okay. Actually, let me check my slope. I don't think I did the slope right. Down 2 over 1. Yeah, let me redraw that. Right, looking at the slope of that piece, it should be going down 2 over 1. It should go right to there. Okay. And that circle's open again because that rule doesn't apply. When x actually equals -1, we're on the blue graph. Okay, so just be careful with those. But watch the open circle, closed circle. Okay, and again, the difference is if you have the equal sign underneath, it's a closed circle. If you don't have the equal sign underneath, if it's just greater than or just less than, you have an open circle. This example, like this graph, the blue piece is going to go on forever this way. Okay, the red piece was going to go on forever this way. So eventually it's going to go through all x values. Okay, it's going to go through all the positive ones on the right, all the negative ones. So the domain is all real numbers. However, the range is not. Okay, look at the y values. Okay, this graph never gets below. There we go. This graph never goes below a y value right there. Okay, so the range for this function is not all real numbers. The y coordinates are never below 0. Okay, and in fact, since this circle was open, they never even get to 0. They just get up to right before 0. So we could write the range of this one would be all y values that are greater than 0, not greater than or equal to. Okay, there's a couple other ways to write that. You can write it as what's called an interval notation. Interval notation is where you put the minimum and the maximum in either a bracket or a parenthesis. And the way it works is, for example, this one would be the minimum is 0. It doesn't get to 0 though, so I use a parenthesis as opposed to a square bracket. I'll show one of those in a second. And the maximum, it goes up to infinity, right? Both of these graphs go up and up and up. There's no maximum. Okay, so that would be an interval. Again, that's not an ordered pair. It's not an XY. It's more like a minimum and a maximum. Okay, so sometimes it's tricky because it looks just like a ordered pair, like a XY coordinate. But you just have to know based on the context if it's an interval notation type thing or if it's an ordered pair. All right, so let's get into some more vocab kind of stuff here. So we have the domain of a function and the range of a function. Okay, so the domain of a piecewise function, let's go to the right there actually, the math terms. The domain of a function is the set of input values. Okay, input values are generally your x values for which the function is defined. And the range of a function is the set of all possible output values, which is going to be your y values. Okay, so with linear functions and even with quadratic functions with x squared, the domain is going to be all real numbers. And if you think about you know, just looking back at our... Okay, so we will not worry about, there's another notation called set notation. I'm just going to skip that one. But let's do one last problem, okay, and then we will do the domain and range and practice one more time, okay? So example A here, okay? Let's graph this one. So it's, again, it's going to be, I'm looking over here first. This is the domain restriction. So I know there's going to be different graphs on different sides of 0. And I know for the x's that are less than 0, the graph is going to look like x plus 2. Okay, so x plus 2, what would that look like? It would have a y-intercept at 2. Now I'm going to do an open circle because, again, this rule does not apply when x equals 0. And the slope would be positive 1, right? Up and to the right, up and to the right. Now here's the thing. I don't want to show that side of the graph. I need to show where x is less than 0. So I need to continue it this way and only graph that piece of it. Okay, and I want to get rid of this other stuff, these points. That's not part of it. Okay, so you can always do that if you want. You can graph it real lightly and then just erase the part you don't want to see. That's fine. Okay, the other rule now, for the right side, when x is greater than or equal to 0, the graph needs to look like 2x minus 1. So the y-intercept's at negative 1. I'm going to color that in because that actually works when x equals 0. And my slope is up 2 over 1. Okay, and I'm going to graph this side of it only, not the left side. Okay, so let's think about, we got our two pieces. Okay, let's think about the domain, the range. Let's see if we can get this figured out. So the domain, right? Between the two graphs, do they go through all values, all x values? Okay, yes, the red piece is going to the left, and the blue piece is going to the right. So the domain you can write a few ways, all real numbers. Okay, or as an interval, it would be from negative infinity to infinity. Okay, that's the way of saying all real numbers in interval notation. Now the other piece, the range. Okay, let's finish the range. Oops, let's get a cool color here. How about we go purple? So the range of this, does it go up and down through all y values, or is there a max or minimum? Well, it looks like the blue piece is going to go up through all numbers, all positive y numbers, and the red piece is going to hit all the negative numbers. So I think this one has a range also of all real numbers. Okay, because again, this piece is going to go all the positive values, this piece is going to get all the negative y values, so combined, this thing's going to cover all values. So again, negative infinity to infinity. Okay, let me just throw one last thing in with range real quick. Let's just say, for example, we had, I don't know, a picture like, oops, let's go back. Let's just say we had a graph that did something like this, and it went down to negative 2. When it did that, let's say it was y equals x squared, and then there would be a minus 2, and that's why it shifted down 2. So the domain and range, okay, just to make sure we're clear with the notation here, the domain and the range. All right, so domain again, this thing's going to end up going, it's going to eventually go through all the x values and all the y values. It's going to the right and to the left forever, so the domain is going to be all reals. Okay, or as an interval again, negative infinity to infinity. But the range, this one has a minimum of negative 2. So you could write it a couple ways. You could say y must be greater than or equal to negative 2. Okay, or as an interval, it's going from negative 2 up to infinity for y values. Now it actually equals the negative 2 at a point. So I'm going to use the bracket, the fancy bracket, not a parenthesis. Okay, you can never quite get to infinity. So the infinities are always parentheses. Okay, and just to show the other end of the spectrum, let's just say, for example, something did this, just so we can see the difference side by side. Let's say a graph was like this, right? Domain and range. range of that one real quick just to finish up. Okay, the domain, this one has a minimum x value, right? It's never going past that. So the x values are always greater than 0, which means it would go from 0 to infinity for x values. Okay, but for y values, it's always greater than -2. So it would be from -2 to infinity. Okay, notice it's not the square brace, it is a parenthesis. Okay, open circle, does not equal. Okay, when you have the equal sign, that's when you get the square brace. All right, so hopefully it helps. And piecewise functions, a little bit of domain and range, and we will be adding to this. So get ready.